This module focuses on non-compartmental analysis of pharmacokinetic data, which is a very useful approach to achieve many of the objectives of our pharmacokinetic studies in veterinary medicine, which include dosage regimen calculation, bioequivalence and bioavailability determination, and the identification of nonlinearities in pharmacokinetics that may occur as a result of dose escalation. Non-compartmental analysis is also called the model-independent approach to analyzing pharmacokinetic data. By model-independent, we mean that a model, which in the case of pharmacokinetics is typically an exponential equation, is not fit to the data. Instead, the data are simply summarized in terms of the maximum plasma drug concentration, which is Cmax, the time at which this maximum concentration occurs after drug administration, or Tmax, the area under the plasma concentration time curve and the area under the first moment curve, and the slope of the terminal portion of the plasma concentration time curve, which is referred to as lambda z in non-compartmental analysis. Here we see the differences between compartmental and non-compartmental analysis in a graphical way. In non-compartmental analysis, we are measuring the characteristics of the data directly. For example, we're looking at the data to determine what the Cmax and Tmax are, and then we're calculating the area under the curve and slope. In contrast with compartmental modeling, we fit an exponential equation to the data and infer the values of the pharmacokinetic parameters from that model. So you may be asking the question, what do we mean by zero and first moment curves? The zero moment curve is simply a plot of plasma drug concentration versus time, which is the curve that we have come to know very well during this course. The first moment curve is that profile that results when we take the drug concentration and multiply it by the time at which it was measured, and then we plot that value versus the time at which the drug concentration was measured. Although it may not seem intuitive initially as to why we do this, think of it as a way by which we weight each drug concentration by the time at which it was measured. So if we have two drugs that have the same area under the zero moment curve, but one drug has a longer half-life than the other, this allows us to distinguish between those drugs. The concentrations for the drug with the longer half-life will be higher during the terminal phase when time values are also higher. This means that the value of the area under the first moment curve will be higher for the drug with the longer half-life. And this allows us to calculate a pharmacokinetic parameter which we call mean residence time, which is the average amount of time that a drug molecule stays in the body after it's administered. We can do this by comparing the value of the area under the first moment curve with the value of the area under the zero moment curve by taking the ratio of the two. The method by which non-compartmental analysis allows us to calculate several pharmacokinetic parameters are listed in this slide. You'll see that Cmax and Tmax are determined directly from the measured data. Lambda z, or the slope of the terminal portion of the plasma drug concentration time curve, is calculated as the slope of the straight line that is fit to the data points from the terminal phase by linear regression after these points are plotted on a semi-logarithmic scale. Then the areas under the zero and first moment curves are calculated using the trapezoidal rule, with which we're already familiar, and then the other calculation we need to know about is how these curves are then extrapolated to infinity, which allows us to estimate total exposure rather than just exposure over the period of time for which we have collected samples. From these initial non-compartmental pharmacokinetic parameters, we can then calculate the well-known or the pharmacokinetic parameters that are already known to us of clearance, volume of distribution, and half-life. And we need to calculate these because these are the parameters that we need to calculate dosage regimens. Using the non-compartmental approach to calculating pharmacokinetic parameters has several advantages. First, we don't need to assume a specific number of compartments. Also, the calculations are relatively simple and can be performed without sophisticated software. Yes, you can do this all in Excel. And then finally, the results are less dependent on when exactly the samples were collected for a particular study, which means that the pharmacokinetic parameters calculated using this approach are more comparable across different studies, and they also don't vary between different analysts or software as much as what they would if we used a compartmental approach. There are, however, also disadvantages to using this approach. Most importantly, we do not have a model that can be used to visualize or predict the plasma drug concentration versus time profile. As a result, it's not possible to predict what drug concentrations would have been at times when data were not collected. Also, it's not possible to predict what the plasma drug concentration versus time profile would look like for different dosage regimens that were not used to generate the data. There are several important points to remember when you design a study to collect data that you plan to analyze using a non-compartmental approach. The values of Cmax and Tmax are highly dependent on when you take the samples. So it's important to take several samples around the time when you expect maximal plasma drug concentrations to occur after drug administration. It's also important to take sufficient samples during the terminal phase so that the slope can be accurately determined and a large portion of the area under the curve does not need to be calculated by extrapolation, because this will decrease its accuracy. The rule of thumb is to take samples for at least 3 half-lives of the drug. Non-compartmental analysis is a very useful approach for comparing formulations and different doses, which is why it is the preferred method for bioequivalence and bioavailability studies. It also allows us to identify if there are any nonlinearities in the pharmacokinetics of a drug as doses increase or vary. The AUC and Cmax will not increase in direct proportion to the increase in dose if there are nonlinearities. However, because we do not have a model to visualize the plasma concentration versus time curve, it's not the preferred method to explore the mechanisms that result in the nonlinearities. Finally, the non-compartmental approach gives us all the pharmacokinetic parameters, clearance, bioavailability, and volume of distribution that we need to calculate dosage regimens to achieve target plasma drug concentrations.